Hi again, everybody. Mr. Kolakowski here. This is a video that's going to cover reflection in mirrors. And as I go through these slides, make sure you jot down some notes. You don't have to copy everything perfectly or anything like this, but the main goal is to give you an overview of how flat mirrors work, the law of reflection, and to give you some examples of how the physics for all of these different interesting, I hope you find interesting topics, plays out, okay? Let's get started. On this first slide, we have obviously a lot of reflections. We can see a mirror, some reflections in the water. This is the reflection off of a CD or Blu-ray or DVD or something. That's a hubcap. Over here, we see somebody taking their own picture from a camera into the mirror. Here's an interesting question. I'm not sure if you've thought of this before. The question is, how does this mirror seemingly know to flip her image left and right, but not top to bottom? In other words, does the mirror have some sort of weird physics behind it where it only seemingly inverts you one way and not the other? It's a really interesting question. I want you to think about that. There's a Physics Girl YouTube video that I will link and have you watch, and I think you'll find that answer and that video very interesting. Let's go to the next slide. This shows us the law of reflection. This is effectively why mirrors, flat mirrors, do what they do. When a light ray comes in, light is a particle, light is a wave. We're going to use what's called this model, this light ray. It's basically going to look like a straight line. You can imagine a photon or particle of light following this vector. You can imagine that the light wave itself is sort of wiggling like this, but that arrow is sort of the average of that movement. This is for a light ray. It could be a laser pointer light. It could be visible light of any particular color. It could be white light, which is really just a combination of frequencies. Nevertheless, this is a model. Models have their limitations. This is a light ray. And the idea is the angle of incidence is equal to the angle of reflection. This theta and this theta are identical relative to the normal line. We've used this normal line before in previous lessons. Notice theta incident and theta reflected are based on the normal line, not based on the mirror itself, which is laying flat on a table as the light ray comes in like this and bounces off the mirror like that. It says at the bottom here very clearly the angles are measured with respect to the normal line. Again, this is the law of reflection, which governs how mirrors, flat mirrors in particular here in this context, work. Why is it a law? Well, this describes what happens time and time again. It doesn't explain anything, it just describes how light waves and light appears to work through experiment after experiment after experiment. There are two general categories of reflection. There's the specular reflection and the diffuse reflection. Think about specular reflection as what you saw on that first slide in that really calm water on the lake or in a mirror. This is where you have a really beautiful flat surface for those light rays to bounce. You can actually see each one of these light rays is behaving according to the law of reflection. In the next type of reflection, diffuse reflection, this is not a smooth surface. This could be water that has been disturbed. It could be a semi-reflective surface like a smooth tile floor that's been polished or a tabletop that's been polished where you can kind of see reflection in it. This is going to be a rough surface reflection. Let's take a look at some pictures of this. This is a still lake, and you wouldn't be able to tell if you took this picture and inverted it, uh, flipped it top, bottom, bottom, top, it'd look fine. You would effectively think the picture is fine. Well, that's because this is undisturbed water. The water behaves like a mirror. It's a flat surface, and those light rays are behaving according to that law of reflection. On the flip side here, we see water that's been disturbed. This is water with maybe wind disturbing it, and you can see some reflection, but if you kind of look over here, you'll see that it's fuzzy. Colors are going to sort of make it through, but it's not like a mirror, and it's a rough surface reflection. This really does, if we go back a couple of slides, this is still following the law of reflection. It's just that that surface isn't flat. So the law of reflection is sort of functioning over a rough surface and causing on our end of things to see a image that's really not super clear. This is a picture of a laser pointer that has been uh, pointed at a mirror, and the mirror is reflecting the light back onto a piece of paper. So the picture on the left here is showing you when the mirror was on the table and the laser pointer light came in and bounced off, you get a really nice dot, just like a laser pointer appears when you use it without mirrors. It's a nice clean circle. But if you take the same experiment, but you get rid of the mirror and you just use a semi reflective surface like a countertop, you can see that the laser pointer light does reflect, but it's diffuse. And that's because the countertop is more rough edged than a mirror. And it causes reflection, but not in that clean circle that you notice from a regular laser pointer dot. It's a fuzzy image. Let's talk about flat mirrors for a second. Here we have somebody looking at a chess piece through a mirror. And here we can see the angle of incidence equaling the angle of reflection. This is the law of reflection right there. What's interesting is the way that our eye accepts that light ray is it extrapolates that reflected light ray back to behind the mirror. So here we see, as the diagram shows, the apparent path of the light ray. So you and I would detect the chess piece back here, at least the top of it here, if we're just using the top of the chess piece as a reference position, that's right there where we would see the top of the chess piece. Our eye is tricked, in a sense, to follow this light ray in a straight line into this virtual image behind the mirror. That's effectively how a flat mirror works in a very simplistic way. Let's take a look at this next picture. A really fascinating question to examine is if you wanted to see your whole self in a mirror, how big would that mirror have to be? Would it have to be the same height as you? Would it have to be like what you see at department stores when you try on clothes and you've got these huge mirrors where you can sort of gauge how the clothes are looking while you're trying them on? What size of the mirror is required for you to see your whole self? If we take a look here, here's the actual guy looking in the mirror. And let's imagine a light ray from the light in the room hits the top of his head and it's reflected. That light ray hits the mirror, bounces off the mirror, law of reflection comes back into his eye. His eye extrapolates that light ray back to his image. This is what he sees from our perspective. If he's standing 4 feet away from the mirror, his image is 4 feet behind the mirror. Okay? That's an interesting idea in and of itself. Now, this is a virtual image, but it's nevertheless what we see. We know that the guy really isn't standing behind the mirror, but that's what we would detect as an observer. The same thing can be done with the bottom of his shoes here. Light bounces off from the room. The light hits his shoes, bounces off, hits the mirror. Law of reflection enters his eye. Now, if you look at this here, we have position X and Y. That's exactly half of his height. You think about this, this makes a ton of sense because if this was a window and you were looking at somebody through a window who happened to be the same height as you and they were standing just as far away from the window as you were, the window being half that size of that as tall as you would allow you to see the entire person. Well, that's what's happening here. So effectively, the object distance and the image distance are the same. The object height and the image height are the same. And interestingly enough, the mirror only needs to be exactly half of your height for you to see your entire image on the other side. So in this lesson, we've looked at this really interesting idea called the law of reflection. There's two types of reflection, if you wanted to kind of categorize it broadly into the specular and diffuse. And as we just saw in the previous slide, object distance equals image distance. If you're looking at a flat mirror, object height equals image height when you're using a flat mirror. And to see your whole image, you really just need half your height required for, as far as the size of the mirror goes anyway. I hope you guys are doing great out there. Keep in touch. Let me know how you're doing. Email me, and I hope you guys are doing well. I'll talk to you again really soon. Take care. Bye-bye.